In this segment, we'll look more at Java interfaces, using as examples two interfaces in the Code Worlds application, displayable and steppable. Now, we said in an earlier segment that if you made every method of a class abstract, you'd end up with an interface, in effect a 100% abstract class, the code for all of whose methods must be provided by overrides in a derived class. There is a specific Java syntax for declaring such an interface, and it's slightly different from that for a purely abstract class. Let's look at the displayable.java file, which has an interface we'll use as an example in this discussion. To declare an interface, you use the keyword interface instead of class, and you don't bother with abstract in the method declaration since that's assumed. You declare as many methods as you like, but they're given no code, just like abstract methods in a regular class. You may also declare final members and static members of methods and include code for the latter. As with an abstract base class like herdAnimal, you can't create objects of an interface since it lacks code for its methods. An abstract base class at least supplies some code, but if an interface like displayable supplies none, then what use is it as a superclass? Why derive from displayable? All you get is the obligation to override getLoc and getVLC, two methods here, with nothing in exchange. Well, you do it because it means that your derived class is a displayable. What you get is the right to be considered a displayable. Stretching the inheritance metaphor a bit, deriving from an interface is like inheriting from a penniless parent, but one who has a good family name. You won't get any money, any code, but you at least get to share the name. You get to be a displayable. Okay, but what's so great about being a displayable? Well, to answer that question, let's look briefly at GridDisplay, which is the class that prints out the text display of the simulated area. I'll repeat that display here in the diagram as a reminder. Now, we won't go over all the code yet, just the aspects that use displayable. So here's GridDisplay Java, and first note the list DSPs here of displayables, which is declared right near the top of GridDisplay. This is the most important member of GridDisplay. The objects on it are what get printed in the output grids. And what objects do you think are in that list? In particular, question 1 here, should we be looking somewhere in the code for a new displayable statement that creates a displayable object to put on DSPs? Why does that not make sense? Returning from a pause, because you can't create displayable objects. Remember, it's abstract, so there's no code. So what objects can be on DSPs? Well, animals for one, and animal subclasses like sloth or cow. But an animal's not a displayable, is it? Yes, it is. Here's animal.java, and look at the header for animal. The implements keyword there is a close cousin to the extends keyword used for deriving from a base class. But implements is used to derive from interfaces. Implementing an interface is not quite the same thing as extending a base class. You don't inherit instance members or instance method code from the interface. You just get a list of abstract methods you have to implement. But very importantly, you also get the ISA relationship. And you can implement multiple interfaces. Animal apparently implements both displayable and something called steppable. That's another interface we'll look at shortly. And note, animal has getLoc and getVLC methods. so it already overrides displayables methods as required. That's why the methods have @override annotations in animal. Now, to be clear, an interface is not a superclass. Animal still automatically extends object, implicitly, as though I'd written extends object up here. Although, as you know, that's not required. It's automatic. And every class but object does have a superclass, regardless of whether or not it also implements interfaces. So, since animal is a displayable, we can put it on the DSPs list here in griddisplay.java. Now, let's look at how DSPs is used in the loops for drawing the display in update down here. This is the method that CodeWorlds calls each time you hit return. Now, the first of those loops iterates through DSPs. It calls getLoc on each displayable, translates the location into a row call index by calling compute index for a two-dimensional array of strings that we're setting up called grid, and puts the two-string result of the displayable into the computed location on the grid at that row call index. The second loop then goes through every row and column in grid, printing each string in it, or printing a dot if the entry is null. That's how we get the textual grid output. Now, as I said, you don't need to understand every detail of that code yet, but do note that all it asks of a displayable is that it have a getLoc method and a two-string method. That's important, and it invites a question. Why don't we just make DSPs a list of animals? This code would have worked just as well in that case, right? Well, to answer that question, note that the displayed grid has a tree right there, along with all of the animals. And let's take a look then at the tree class. It's not a subclass of animal, note, but it does implement displayable. So we can put trees onto the DSPs list along with animals, and the display code, the update code, will work just as well with either. And of course, if some new kind of entity were to be added to the simulation in the future, all we'd need to do to make it work with the grid display is to make it implement displayable. This is a very powerful idea. An interface provides a means by which a variety of classes may be considered to be of the same type, so long as they meet the criteria established by the interface by implementing the methods defined in it. Tree implements getLoc by returning its location, but it implements getVLC, interestingly, by returning a default zero-valued vector. Trees don't move, of course, so it makes sense that they'd have a velocity of 0. Each implementing class may override the interface methods in its own way, as long as it makes sense. And by the way, the getVLC method in displayable isn't used in grid display. Why does displayable include that method? Because we'll develop various forms of display in the future discussions, and some of them will want to display the velocity of the objects. When you define an interface, it's important to keep it flexible enough that it can accommodate future changes and improvements. Okay, so the CodeWorlds simulation calls step on each animal. Remember that method. To advance its state by one simulated time unit, right? And as we add to the simulation, there may be other classes that also must be stepped, but are not animal or a subclass thereof. So we define interface steppable. Now, this requires that any implementing class have a step method. Any class needing stepping must implement that interface and override the step method. Animal implements steppable, as we saw a little bit ago. And tree, by contrast, does not, since it doesn't change and it needs no step. And then in the code world's main, we can declare a STPs, steps list of steppables, which might contain a dozen different types, all unrelated except by the fact that they all implement steppable, and thus each one is a steppable. And then further down, we can have a loop like that runs through all the steppables of whatever type and calls each one's step method. Now let's step back a minute and look at kind of a bigger design point here. Broadly speaking, there are two ways one can use inheritance. The most obvious and usually first taught is to inherit a base class's methods and members and to augment or override them. Such use is termed implementation inheritance because its main purpose is to inherit and adjust an existing implementation in the base class. Our margin vector is a good example. Almost all of its code came from vector, with just a few tweaks added by margin vector. And another example would be cow and horse. They get almost all of their code from a herd animal, and thus are good examples of implementation inheritance. But another use is that provided by interfaces in Java and by similar features in other languages. In this use, termed interface inheritance, the implementing class gets no members or methods from the interface, as animal, for instance, got none from displayable or steppable. Rather, it gets typeness, the right to be a particular type, like a displayable, in exchange for providing overrides of the methods in the interface. Any class can be a displayable, as long as it provides a getLoc and getVLC method. And those methods are all that grid display, recall, needs, in addition to the toString that every class automatically has by inheritance from object. A class can represent a tree, an animal, a human, a building, whatever. And as long as it has some reasonable implementation of getLoc and, for future possibilities, getVLC, then it can be a displayable. And it can be put on the DSPs list along with all the other displayables for grid display to print out. Interface inheritance also allows a class to be many types, as we saw in animal, to implement many interfaces. Just as an example, look up the Java docs for ArrayList, class we've been using, and count how many interfaces it implements. And returning from a pause there, you can see in the docs, it apparently implements serializable, clonable, iterable, collection, list, random access. Each of these interfaces specifies some small set of methods that comprise a type of behavior. The iterable interface, for instance, requires an iterator method like that returns an iterator, and that's all it requires. It describes a collection that can supply an iterator. And as we already know, iterator is an interface describing an ongoing iteration with its next and has next. We didn't get to remove, but we will later on. Of the two uses, interface inheritance is by far the more powerful and important. A good OO design will define dozens of interfaces, each specifying a usually small set of methods that is the essence of some kind of behavior, like displayability, or able to provide an iterator, or able to be time-stepped. By chopping behaviors into small pieces like this, and providing interfaces that allow different classes to be a type that provides each behavior, we can write code like grid display that expects a particular interface, and only that, a particular specified behavior, and then we'll work with any class that implements that interface.